Oh, thank you very much for having me here. Well, I'll be talking about the Magellanic Clouds. I think that what Gemini is doing for the science case. So first of all, I'd like to thank very much for the SOC and for the LOC for having me here. It's a real pleasure to be back to a Gemini conference. Actually, that brings me some memories. In 2007, I was a student, and the second Gemini meeting was actually my very first international science conference. That was the way of my advisor to show me how the astronomy world works. And I was quite pleased to see that, and I'm here now. So thanks to your community. You can recognize some faces there. Okay, so about the Magellanic Clouds. Okay, so what do I have to say about them? So the southern hemisphere is very interesting because you have the Milky Way bulge, you have the Magellanic Clouds. So why is this so interesting that brought a lot of attention, a lot of investment to build a lot of telescopes here in the southern hemisphere? So in the 70s, there was this large map of the whole sky that traced the gas, right? So they found this beautiful, what is called now the Magellanic Stream, that's actually that trailing structure that's left behind the orbits of the LMC and SMC around the Milky Way, right? A few years later, there was a confirmation of the leading part that's actually crossing the Milky Way disk in the line of sight. So that was kind of difficult to prove, but they got it right. So the beginning, so when you have only the trailing structure, you can think about the room pressure stripping. That's only gas interaction between the halo of the Milky Way and the SMC. But when you have the both kind of opposite structures there, then you have gravity and tides taking place. So if it's moving the gas, it's also moving stars, okay? So this is what we are looking for now for stellar populations. That's kind of fitting in what I'm saying later. Right, but even if you think about tidal forces, tidal stripping, it's not straightforward. How did the LMC and SMC ended up in this configuration nowadays? So there are still two very independent and completely different paradigms. The one on the left here called the bound scenario, that's the classical, the canonical scenario that says that the LMC and SMC, they are bound to the Milky Way, meaning that they are dwarf satellite galaxies that are orbiting the Milky Way, and their orbits kind of synchronized. So now they are a pair of galaxies. And there is this new, relatively new from 2007, the PhD thesis of Ugurtina Besla, so saying that the LMC and NMC, they are kind of a pair, binary pair of two galaxies that are in their first fall to the Milky Way. So they just arrived to the Milky Way vicinity, right? So they're completely different, but still both ideas, when you go to simulations, they can reproduce kind of the whole general broad view of this gas stream. So the leading arm, the Magellanic Stream, but there are still few things like fine-tuning the very specific position of the two galaxies, the double filaments. And if you see here on the left, you see that there is like two filaments coming out here from this simulation that's kind of seen in the observations that's not reproduced by the other and so on. So there's still some steps there to really find what was the past of these galaxies, right? So here I list a few observational evidence that kind of support one on another and some discussions here. So this double filamentary structure in the Magellanic Stream is actually real. So there are some studies showing that the kinematics and the chemistry are different and they match the LMC and SMC. So apparently the gas is pulling out from the two galaxies, right? So the bound scenario, the classical scenario, can reproduce that with simulations. And the first and false scenario says that could not, but apparently they argue that it depends heavily on the initial conditions from the SMC. So it's really important to know how was the SMC at the beginning, because now we know that the SMC is really disrupted structure and then has a line of sight depth that's huge and has tidal arms and streams everywhere. So how was the initial conditions? This is an important question, but the answer is not trivial. And that apparently causes a lot of impact on the results from the simulations. Another prediction here is the LMC local wake there. So this is a prediction from the first in fall scenario saying that, okay, basically if you have the LMC that's really massive falling into the Milky Way, so when it passes through the stellar populations, the outer halo, it will cause some disturbance there and will cause some local density of stars. And that was recently found by our observations, right? It was Nature paper last year. Okay, so this was a prediction and a confirmation of observations. And another topic that's very interesting is the plane of satellites problem. So the lambda CDM cosmology predicts that we have dwarf galaxies surrounding large galaxies. Okay, but their orbits should not be organized as a plane, should not be very tight organized. But the observation shows in the Milky Way and another two galaxies that dwarf galaxies are actually organized in a plane. And by coincidence or not, the LMC orbits are matching the kinematics and the position there of this vast polar structure, for example. So the question that remains is the LMC the cause of this vast polar structure or not, right? So the bound scenario, the classical scenario says that, okay, if you think about the LMC and SMC orbits kind of synchronized, so why not the other galaxies as well? So they could synchronize and they are in this. Personally, I think that's a long shot, but there is a paper discussing that. And on the other context, there are some simulations thinking about the LMC bringing together the SMC to the Milky Way, along with other smaller dwarf galaxies. And there are some simulations showing that, and the observations from Gaia. So we have these proper motions, parallaxes, beautiful data. So there are some studies there that already confirmed like 4 dwarf galaxies that belong or are compatible with the kinematics and positions of the orbits of the LMC. So apparently the LMC could have brought a small system of galaxies to the Milky Way. So that's pretty interesting. And then other details from the simulations that you need to consider some mass for the LMC. So usually the classical models, all the simulations assume like a lighter mass, and the first in fall scenario assumes a heavier mass. And there have been many recent studies with different observational evidence showing that the LMC is actually heavier than previously thought. So it kind of endorses better the first in fall scenario. So also the potential for the dark matter that they assume it's simpler in the bound scenarios is more realistic in the other. And the proper motions is another source of uncertainties here, because the classical scenarios, the simulations, they use usually the ground-based proper motions that have a large uncertainties, is less precise. There's some discussion there on the accuracy, but well, let's leave it there. So the space-based proper motions have a better precision there. So I see some more green here on the left. So I think that the first in fall scenario is winning this thing. So it's gaining a lot of attention recently, and that's the current paradigm recently currently accepted. Okay. Right. So the Magellanic system is in its first in fall there, right? And we know that it can reproduce the gas structures. We have these two evidence and some scenario to explain it. So the next step would be stellar populations, right? So if gravity is taking place, is moving away gas, it should move also stars. So where are those stars? So the main surveys covering the large area of the sky, it's large. Denise just said, right, the SMC is huge. So if you want to cover this, not only the SMC, but the LMC and the string and the 200 degrees, it's a lot of work. So there are many surveys that are complement each other in wavelength and variability and area of coverage and so on. So I just like to point out a few of them here so we have an idea. I am particularly interested on star clusters. And I try to put in my our work here on the Vizcacha survey that's concerned the star clusters specifically. So why the star clusters? To trace the stellar populations of the Magellanic Clouds and what information they can bring here, right? So the idea is that star clusters are very good standard candles. So you can measure distances if you have their photometry very well. So if you have a population of star clusters around the Magellanic Clouds, you can trace their standard structure. So we have the 3D structures of these galaxies, right? On the top of this, we can have their ages. So we have a timeline, right, of the past history and 3D structure. So it's great. So you are building up only using these guys as fossils. And also we have the metallicity, so we have the chemical enrichment history, and on top of this, we have also the opportunity to do kinematics. So that's where Gemini will fit in. I'll show you in the next slide. And on the top of all of the things that you can have the structure of the galaxies using the star clusters. The star clusters themselves, their internal structures, they have their internal evolution, okay, because of the interactions between the stars. But this internal evolution sometimes can be affected by external forces, external effects. So we can use these internal characteristics of the star clusters also to trace something that happened in the Magellanic system, okay? So the idea here is to end up with a 3D map of the star clusters, tracing everything that we can use in these star clusters, right? Okay, so just go to the current surveys, right? So Bruno, come on, just go there, take the data. Don't need to apply for more telescope time. It's expensive. Leave time for the others. Come on. No. So yeah, but no. I'll show you why. So the idea here is I show the limiting magnitude of the current surveys and the image quality that you can reach with these surveys. So you can see clearly the jump between the 2-meter telescope size based surveys to the 4-meter ones that's jumping photometric depth. So you can reach actually in the color magnitude diagram, you need deep photometry to reach the oldest stellar population. So where you can measure ages, okay? But the thing here is that they're all ground-based and limited by atmospheric turbulence. So for the core of the star clusters, it's not useful. So you cannot do properly a photometry of the star clusters themselves. These surveys are great for a general view of all the field stars, stellar populations, variability. They have a lot of results that are very interesting, but for the star clusters, no. So you could go to space. So Gaia would solve it, because have everything, but it's shallow photometry. So it just read barely the red clump stars and maybe the top of the main sequence for younger star clusters. And HST could do it, but for a large program, like very many clusters there that are not super beautiful as the globular clusters, many stars there, it's not feasible. So the compromise we found with the Vizcacha that comes to the rescue here is using adaptive optics in a 4-meter telescope with a solar telescope in the Neural Lab. So the idea is that I can reach like 0.3, 0.4, 0.3, 0.5 arc seconds maximum in the I band. And I show here, it's blinking. So the difference between the image in the core of a star cluster. So this is the image of one example from the Vizcacha survey. And here a comparison of the core with and without AO between, like an example, the Vizcacha and the SMASH survey, okay? So you can imagine here how it would be like with an 8-meter telescope, it would be great. And if I compare directly the color magnitude diagrams here in rings, okay, so you can appreciate here that in the outskirts of this region, the photometry with and without AO, they are comparable. High quality, deep, and that's fine, as expected. As you go down to the core of the star clusters, so we really need this adaptive optics to solve, to find this compromise if you want to study star clusters. Okay, so just a brief summary of the Vizcacha survey, some statistics here. So essentially have more than 40 members working nowadays, and more than 200 clusters observed so far, and 80% completion. This is the photometric part. So right now, I think it's a bit difficult to open the dome, but I hope that by September, the weather will be better for when the Magellanic Clouds are up on sky. Gemini is just a neighbor, so I think that will be difficult, but on September, I think that will be fine as well. So Gemini jumps in here for the spectroscopic follow-up. So we are using GMOS. Okay, so in a large program, no, not a large program properly, but we are applying for time for three national program with the three different tags. So I have to manage all the three countries there and then get the time at the end. So you know the drill. Okay. So the GMOS, we are using the calcium triplet spectroscopy for moods with masks there, right? So you can get metallicity and radial velocity. So we get the component on the line of sight for the velocity. So remember that from the photometry, I already have the 3D positions. So the goal here is to have the 3D velocities. So we get the spectroscopy from calcium triplet that's actually cheap because they really have your strong lines. And the proper motions you get from Gaia. So we have all the phase space vector completely for the motion here. Okay. And well, as a byproduct, I produced this like distortion map of the GMOS field. I talked to Herman Jimeno. He said that it was not done this kind of detail before, so this is useful. In the center is okay. In the corners as known, right? It's a bit distorted, but it's about like maximum 2 arc seconds. So we don't care. In the center here, that's useful for us. It's okay. Then the Gaia proper motions. Right. So I'll just send those one example here of science case. I have many others if you want to discuss later. But for the sake of time, I'll focus on one example here that where the Gemini data were crucial for results. And so this first info scenario, there were some simulations there in 2012 that predicted that about 150 to 100 million years ago, there was a close encounter between the LMC and SMC. So they are a pair of galaxies, but they are not like strongly, they kind of oscillate, right? Their relative distance, they oscillate. So about 200 million years ago, they have a different directly shock there. That caused some distortions in the LMC. So the LMC is essentially a disk. So it's tilted on sky, but caused a warp. And on the SMC, it caused a bridge. So this bridge, same drill as the Magellanic string that was really big. For the local structure there is the same thing. So it caused some stripping of gas, but also of stars. So for the LMC, when you see it edge on, so this me holding the LMC here, a reference. So the LMC is like 50 kiloparsecs and from us, and the LMC is 60 kiloparsecs from us. So the LMC is tilted on sky like this towards the LMC, and the warp is more or less like here and towards the SMC as well. And the idea is that some models predicted the warp, the observations confirmed it with this mesh survey, and we're looking for the star cluster. So is there any signature there that we can find the warp? So the distances themselves will come in the next paper. We already have the results, but I will not spoil them here. But we studied the internal structure of the star clusters here, and then we found something that is really curious. Here, essentially, the colors of the star clusters don't bother about the details. They only show the region here around the LMC, right? So the red points here shows the clusters that are around the LMC warp. And they show a larger dispersion in the internal structure of the star clusters. And we don't know why. We didn't expect that. So this is something interesting that we found. And we are looking for further investigations here to understand which kind of external forces, if any, could have been affecting the internal structure of them. So the SMC, and that will be my last point. The SMC, the structure is kind of more difficult here. The bridge here and the contours are gas. Okay, so you see that this orange part, yellow part here, is the heavy bridge of gas. Okay. And the red and blue points are from this study here using Gaia data that shows with some selection that the red points are younger stellar populations that matches the gas, meaning that when the gas was pulled out, it was forming a star, so that makes sense. But there was also a discovery now of older stellar population that's forming a bridge here towards the south. So that's very interesting because the stars were already formed by the time when the bridge was formed. Okay, so this was pulling down. If I go to the beta catalog, that contains some heterogeneous age compilation from literature, but still can see some relations there. We see the two bridges of younger and older stellar clusters, and we found that there is a third ridge to the north with intermediate age stellar clusters. And here with the full phase space vector for a shorter sample for starting, we studied exactly this northern bridge and the opposite side, and we found here that they are moving away. So not only they are aligned with the direction between the SMC and LMC, but these clusters are moving towards and away from the LMC. So this is clearly, I interpret it, it's clearly, it's moving. So as the bridge and the counter bridge structure, so these two tidal events here. And for the future, here there are many other telescopes and instruments following up this. But I would say that they are broad in general for the field stars, for gas and stellar populations. For the Gemini, what I think is that's playing this role when the star clusters, for example, like follow up specific targets going very deep. So adaptive optics going deep photometry, core of the clusters, spectroscopic follow up. That would be my goal for the very near future, present, I would say. Maybe like high resolution spectroscopy, we're seeing ghosts there to do stellar populations, really heavy chemical evolutions and so on. I leave you with my take-home message, and thank you for your time.
Thanks, Bruno. Is there any question from the audience? No? Slack?
Yep.
No? Okay, I have no questions because I part of the project, but I would like to make a comment, and I would like to emphasize the importance of the synergy between photometry and spectroscopy, because if we want to understand the chemical evolution of the SMC or any galaxy, we need to know a lot of things, metallicity, ages, distances, but that is not enough. We need radial velocities and metallicity with the accuracies of that the spectroscopy can give us. So for us, it was very much important to have the possibility to observe star clusters with a lot of star clusters with the same instrument, with GMOS, and it was a complement of the Vizcacha survey, very much important. So I would like to emphasize that the possibility to observe a lot of clusters with the same instrument is something very important and necessary. Okay, questions?
Nice talk. I wonder, you show the work of the Magellanic Clouds, and I didn't have a clear which is the model that is supporting this work. Is the bound or the infill? And another related question is, what do you think is the more appropriate model for explaining the formation of the large Magellanic Clouds and the association with the Milky Way?
Yeah. Well, this model here is from Basler 2012. That's the first infall scenario. So there are some simulations there that produce this. Well, personally, I was tempted a lot of time to follow the classical scenario, because they have collected a lot of evidence, not only in the structure, but also chemical evolution, stellar populations. There are lots of other evidence that we're trying to match for a long time, many decades. So there are some evidence there for the classical scenario. So I was kind of defending that until a while ago. But now I'm turning to the first infall, because there are new evidence now that are more compelling, and then more accurate data, and they're getting creative in independent evidence. So I think that's key. So when you have independent information there from different predictions, and then you can prove that with observations, I think that's supporting a lot this first infall. But there's still a lot of open questions for them to answer, because they still have to run models to explain everything that the classical scenario explained before. So there's still open questions that, yet to be answered. So let's see as the next chapter now. So we are, in our side, we're keeping collecting evidence on the side, for example, for the SMC structure. So they really need that for the initial conditions. So with the star clusters, we hope to have some hints on that.
Okay, I
I
think,
have a question.
okay.
Quick question. Okay. This is Songcho from Kasi. What I'm curious about in the LMC system is how your the first info scenario and your dynamical model and observations that supports or explains about the age metallicity gap in the LMC star clusters.
Yeah, that's a very good point. I have not seen any of these yet. I think that's one of the open questions that I want them to explain, but there is none, no model so far. But that's very curious. For those who don't know, the age gap he's talking about is that the LMC has stars, field stars for all ages, but star clusters have ages from young down to 3 billion years, and there is a jump. And then you don't have any clusters between 3 and 10 billion years. And then you have older clusters that are similar to globular clusters. So this is a puzzle that is one of the questions that we try to solve with the SCATCHA survey on the goal of the mass of the cluster. So the very massive clusters are studied and define the LMCH gap. And the field stars do not present. So what happens in between, like the intermediate mass star clusters? So do they show some intermediate transition, something? I don't know. So we are trying to answer this with the SCATCHA survey, for example. As for the models, still to see.
Okay, we don't have more time for questions, so let's thank Bruno again, and coffee time.